Okay, today's talk is about support vector machine and boosting. Basically, we go back to the problem of classification and introduce some new loss functions. Previously, we talked about cross-entropy loss, but now we introduce some other losses, two new losses, one of them based on some kind of geometric interpretation. The other is kernel-based method, which is a way of doing kernel feature expansion without actually explicitly doing that. And then later we talk about the concept of weak learner, additive models, and boosting. So yeah, that's the kind of summary of what's happening today. Let's start, or continue actually, with binary classification with linear model. The idea is we know the binary classification. Here the only difference from before is that instead of considering targets to be positive 1 and 0, we consider them to be -1 or +1. And this is just for algebraic simplification. There is nothing inherent in this labeling. So what was the linear model? The form of linear model was we compute first Z as a multiplication or inner product of W and X, weight times X, and then we add a basis, or sorry, bias term, and then we compute the sign of it, whether it's positive or negative. We say it is class +1 or class -1. So, and the question that we want to address in classification is that, or in general in machine learning, but here as well, is that how we should choose W and B. So we talked about this. Sometimes we don't mention the bias term B because it is already incorporated in the weights W if we change X properly. But that's not very important here. So we saw 0-1 loss function before. So 0-1 loss function has some form like this, that when the target or prediction is the same as target, there's no loss. Otherwise, there would be loss of 1. And then what we did was basically saying that find weights that minimize the sum of loss function over the training data points. So that's the kind of the goal that we want to achieve, but that was computationally expensive or computationally difficult. So for example, we didn't have gradient for this loss function, so we didn't have an easy way to compute it. And also another problem with it is that it doesn't distinguish different hypotheses. And by hypothesis here, I mean different models that are described by different weights that achieve the same accuracy in any way. This will become a bit more clear in the next few slides, what I mean. So if we just use 0-1 classification loss, and even if we train it to minimize it, there might be many different weights that have the same 0, for example, loss function, but that loss function doesn't say which one of them is better than the other. And that would be an issue when we go to the test error, or when we want to compute our classifier on a new data and compute the test error. In that case, not all weights or all hypotheses with even the same training error would be equally the same. So what we did was investigated some other loss functions that were easier to optimize. For example, we considered logistic regression, which had a kind of logistic activation function and a cross-entropy loss function. Here the plan is to consider a different approach, starting from the geometry of binary classifier. Okay, suppose the setting is like this. We have this data, these stars and circles, blue ones and red ones. So each of them belong to different classes, class -1 and class positive. And then we want to find a line or classifier, linear classifier that separates them. Okay, maybe one question. How many lines can we find that separate this? Maybe I just start with one of them. Okay, someone said infinity, right? Yes, exactly. So we can find infinity different lines that all of, oops, that wasn't really separate. suppose all of them are lines. So all of them can separate these data. Now the kind of question here is that, and I get back to it in a few slides, is that which one should we choose? Do you have, okay, so do you have any idea which one should I choose?
I would want kind of perpendicular to that. Sorry. When is the furthest distance from all points? Makes sense, so that you're less likely to like one point end up on the wrong side.
So okay, so the answer was choose the one that is further from each of the other points, from each of the classes. There is another.
Maybe one statement classification works in another. To the set for which you are opaque or more opaque.
Okay, so the answer was that choose the one if making error for one of the classes is more okay than the other one, choose the line to be closer to that class. So that's also a good point. But consider here that the costs are both the same, so we don't prefer between them. So we should specify the loss criteria. So that's the answer here. So these are all good answers. Let me move through this and it becomes kind of clear. Let's try to formalize it a bit more algebraically. So the decision boundary basically looks like a line here. And it's described by some kind of linear equation. So here, the formula for the line would be something like this, that W transpose X plus B should be equal to 0. So this defines a set of X's, points that are on the line. And then we can say that the points on one side of them would be points that satisfy, for example, positive, and here the same thing to be negative. So these are the kind of the geometry of the space and this line. So here I showed it as a line because it's a two-dimensional space. So because X is belonging to R2, but if it belongs to RD, then this line, you should think of it as a hyperplane, D minus one dimensional hyperplane. So if X was R3, it would be a plane, and then more than that, it would be a hyperplane. And as already kind of it's clear from the picture, the points on hyperplane are described by function f of x, or points that are W transpose x plus b equal to 0. So this function f of x, which is also a function of W, takes value of 0. And then points on one side would take values that are positive, takes on the other side would take the values that are negative. Okay, is this clear? So I think this should be, probably you have seen equation of line and hyperplane before. Okay, so now knowing this, the question is how we should find a hyperplane that separates the data points. So the idea here is that, okay, so one side is positive, the other side is negative, that function. So data points, if we choose W, okay, such that data points with positive labels satisfy f of x being W transpose x plus b having positive value, and data that are having negative label have the same thing but with a negative value, so the other side of that hyperplane, then such a W satisfy our criteria. So they separate, it defines a line that separates the points. We can basically write this in kind of intuition, or these two cases, in a form of a linear program. It's a feasibility program here, which basically says that find W and B that minimizes 1. That 1 doesn't matter, it's just like a constant. So this is would be a linear program that finds only has the objective is constant, but has a set of linear constraints. So what are the linear constraints? Exactly as what we had before. Well, almost exactly as what we had before. We say W transpose Xi plus B should be larger than +1, some just arbitrary positive number, for data points that have target of +1. Or we could say that for the points that are negative labels, we set this to be smaller than -1. This +1 or -1 is at this stage is arbitrary. We could choose it with any, say, +C and -C for C that is positive. So that would be the same. So here I just chose C to be constant equal to B1. Yes?
Why can't it be 0? And then how long does it less than instead of less than?
So I guess the reason that we don't want it, yes, we could have it 0 and then instead of having greater or equal, it would be greater or less. That would be fine. But I just wanted to use inequality that has equality as a part of it. But in that case, if we choose, if C is equal to 0 and it is the same form of inequality, it would be, it can choose points that, it would be confusing for points that are on the line. Any question? Yes.
Why we're optimizing one?
So this is a feasibility problem. So so the feasibility problems here basically says that I want to find a W, and so the question is that why? Okay, sorry, I forgot. The question is that why we are optimizing one, and the answer is that this is a feasibility problem. It doesn't. What matters actually just the satisfaction of constraints. So we can choose any objective, including the value to be 1, the minimum of 1. So this tries to find a problem or W's that minimizes the objective, but the objective is constant, so it doesn't matter, such that the constraints are satisfied. The constraints are linear, so this is a linear constraint, and the objective is linear or constant even. So that would still be, then using this we can formulate it as a linear program, which is have a kind of linear objective and linear constraints. Yes?
You know, when we're not even optimizing it, we just want to know one solution for that and that's just solving that.
That's right. Yeah, so we just, the comment is that we just solved that. I'm just saying that if, I mean, in optimization kind of packages or optimization, the different types of optimization problems, I mean, they have different names like linear program, quadratic program, and then you have packages for solving them. I'm just saying that if you want to solve this, you can formulate it as a linear program and then use a linear program solver to solve it.
You could formulate linear regression of this as well.
So we could use linear regression as well. So
we could formulate it just like this one, minimizing one, subject choose, and then the linear regression itself. Like the weight times x equals to y.
Right.
And then you're just solving an equation or
yeah, but I think if we asked it to be exactly to be positive 1 or to be negative 1, it would be too restrictive. There was a question there, is it? Yes.
I should like to comment that instead of one, so we can use any constant.
Yes, any positive constant, yes. Is it just arbitrary, just an example? Yeah. But I get back to this later, and then I can actually modify this formulation, so it becomes kind of more clear why I started from this point. So the question is, how can we minimize the cost not cost independent of parameters? So this is the cost. So So still, this whole objective, like this is a constraint optimization problem, which basically says that let's minimize the cost while constraints are satisfied. If the cost is trivial, like 1, then that part is not an issue because it's always minimized. But the constraint part might not be might not be satisfied. So the solver still has to find a W that makes that while W, this constraint is satisfied to be true. So that's the part of it. So this is just a formula this is a form that people use to write something called feasibility program or problem. And we can formulate, we basically put everything that we want all in the constraint. Okay. As I mentioned before, so this solution just gives one W, but there are many, many different, infinite number of ways that can separate these points. And the question is which one to choose. And you gave some ideas before. So here the idea is that something that is called optimal separating hyperplane. So optimal separating hyperplane is a hyperplane that separates two. Okay, separates two classes and maximizes, okay, so that's important thing, maximizes the distance to the closest point from either class. So in other words, it's called maximize the margin of the classifier. So maybe let's look at it, what it means basically. So suppose this is the kind of line that we selected. So this line has a distance to each of the points. So there is a distance to this point. There is a distance to each of these points, say some number, okay? And similarly, we have distance to the red points. So what we are doing is that, okay, so one of them, on each side, we have a minimum distance. So one of, for example, I guess either of these, this or that, has minimum distance on one other side, and then I guess for this side we have the minimum distance to the red case, red points, so red circles. So here the idea is that we try to find a line that the minimum distance to either of the classes is maximized. So for example, if I selected different lines, so for example, if I had a line that was like this, okay, I guess that was a bad choice of color given the background is orange. But here you see that, well, the distance of this distance would be large, but this distance would be small. So that's not a plane, hyperplane that maximizes the minimum distance to either of the classes. So this is the idea of optimal separating hyperplane, optimal in the sense that it maximizes the minimum distance. The reason that this is a useful thing is it usually leads to classifier that generalize better on test data. And the intuition why this is the case is that is something like this. Suppose we have, I'll try to clean this. So the intuition is that suppose we have some other data points that we haven't seen, but it's coming from the same distribution, class -1 and class +1. So for example, there would be some points that are if we have a bunch of other samples, we get data points like that. So we haven't seen these things, but there exists. So if the hyperplane is very close to one of the sides, the chance that, for example, if the hyperplane is here, the chance that many of these other kind of orange points, or red points actually, falls to the wrong side of the classifier would be increased. So here we want to be as far away from each of the sides, so that the chance of a new data point being on the wrong side of the classifier would be minimized. So this kind of gives an intuition of why this might be a good idea. But the end result is that if it minimize or maximize this margin, the classifiers usually generalize better on test data. Okay, any question about this idea? Okay, so there's a question. Is this maximize minimum distance related to minimize all distances? Well, I guess you need to define what minimize all distances mean. You mean the sum of all distances? Because all distances, we have different numbers for each of distances. Here, we are maximizing the minimum distance. But say we are not minimizing the, for example, the sum of all distances or something like that. So distance of each point to the plane. You mean so it should, again, I guess it should be like this, minimize all distances. I mean, you minimize the scalar. How do you convert distances of each point to the plane? So that's the issue. Okay. Any question? Okay, so here let's try to talk a little bit about kind of the geometry of points and planes and distances. Specifically, we want to talk about the distance of a point to a plane. So the distance of a point, so if you have a plane that is defined by f of x, b plus w transpose x, so any point on this plane has a distance 0, of course. But if the point, we have a point x prime here, the distance of it can be calculated to be equal to w transpose x plus b divided by the L2 norm of w weights. So that's, I guess you can prove, I mean, of course you can prove it, but I'm not going to prove it, but that's a property of the distance of a point to a hyperplane, how to compute it. That would be the equation for it. And the other thing that is kind of maybe important is that here we have some vector w star, which is essentially a vector that is defined by normalizing the vector w. So this would be a vector that is computed based on w divided by the norm of w. So as a result, the property of it is that its L2 norm is equal to 1. So this is a vector that is of unit size and can describe the plane. And the same hyperplane can equivalently be described in terms of W star, because hyperplane essentially has a direction. The difference, if I multiply W by a constant, we still have the same hyperplane. So for example, consider just we have W transpose X, so it defines a set of hyperplanes. I define W transpose X to be some constant W with a positive constant. This hyperplane, which is equal to C, there's a transpose here too, C transpose X equals 0. These still define the set of the same set of points, and also the same, if C is positive, the same side of them, positive side and negative side, defines the same half spaces in RD. So essentially, this shows that if I multiply some W by a positive constant, the geometry of the plane would be the same plane. So it is just different scalar value of that W. So one idea here is that maybe we can normalize the size of W's, only work with W's that have norm 1, and that would be W star. Yes, there's a question. Just give me a second. Yes, Ahmad, I guess.
So if so if the hyperplane's formula is not W transpose X equals to 0 and it has a B term, a constant term, then we would have to multiply that by C2, right?
Yeah, I think that will. Yeah.
Okay.
Yeah. So the question is that if you have B, not just in a plane form, but we have a B, what happens to B? And then B should also be multiplied by same constant C to define the same hyperplane. Yes. Right. I think so. I couldn't really hear from the far, but
yeah, I think that's just the rescale formula for the time.
This one?
No, the plane itself. Yeah.
This one? No.
No, the other one. W transpose X by 1. That would be the equation that instead of taking the normal vector, the W, you take it to the normal vector. It wouldn't be the distance from X prime.
Right. Yeah.
Oh.
Okay. So okay. So we had the distance of a point, or a signed distance of a point for hyperplane as we have here. So this would be W transpose X prime plus B divided by the norm of W. So this is a signed distance because if things change and becomes like on the other side, the value becomes negative value. Okay. So this is good. Now we can go back to our classification problem and try to formulate it as an optimization problem. So recall that the goal of classification was to find for the ith data point, it's correct when the sign of W transpose Xi plus B is the same value as the target. So if the target is +1, this should be positive. Vice versa, if this is the target is -1, the W transpose X plus B should be negative. So this can also be written as just this constraint that W transpose, sorry, T targets of data point I, which is scalar times the other scalar, which is W transpose Xi plus B, should be always positive. And this is clear because when this is positive, positive 1. So when this is positive 1 and this is positive, then it is positive. When this is -1 and this is negative, this should be negative. This should be positive. Minus times another minus. So this is another way, this kind of inequality, to describe what a correct W should be. Correct W that classifies a point correctly should satisfy this inequality. And we can also talk about the distance. So we can also normalize it and basically talk about the distance to be larger than some constant C. So what we are doing here is that saying that Okay, so this is the same equation as before, but then we have a normalizing by W, which basically makes it a distance. And then we are saying that the distance should be larger than constant C. So this basically means that if W satisfies this, it correctly labels the data point and has a distance larger than distance C. Yes?
Expression, the W transpose X over the norm of W. Is it the distance between the point and the plane?
Yes.
You said it was, right? In the brief?
And that there was no point for it.
Right. So okay. So yeah, I guess maybe I didn't hear you. So there is a prime here. If
Oh. Okay, good. Thank you.
so, is it clear?
I think so. Maybe.
Okay. So if you believe that this is the equation of the distance of some point x prime to a plane, then what we have here is basically saying that they compute the distance, and then so it has some distance, and then the distance first should be on the right side of the plane because of this multiplication by ti, and then the distance should be larger than c. So this essentially, this constraint, all it is saying is that. Okay. So what was the goal though? We wanted to minimize, maximize the minimum distance. So what it means that, okay, so let's try to write it. So the distance of the d-ith point to hyperplane, which is described by W and B, we just use the same formula as before. So it would be this distance, and then we have multiplication by ti. So if this value di is positive, then this basically means that we are on the right side of the classification or hyperplane, the same one as the target suggests. And then the distance, whatever it is, the value of it is the distance to the hyperplane. If di was negative, then it would mean that W is incorrectly classifying that point, because the target, for example, T is negative, but the distance, the sign distance is positive. So it's a wrong direction. So maximizing the margin is basically saying that maximize the minimum distance of points to the hyperplane. So I can compute this as compute the minimum distance for I equal to 1 to n of di, and then maximize that value by searching the space of W's and P. So this is essentially saying, this is kind of formulate maximizing the margin as an optimization problem. Of course, now we can replace the i's and kind of expand it. What I want to do here is kind of use a small trick to get to another equivalent formula. Yes, there's a question.
Yeah, so d sub I, that is the distance, right? That is not the sign. The sign distance is without the t.
So it is distance that is multiplied by the target label. So if it is positive, it means the distance is that value, and also it is on the right side of the hyperplane. If it is negative, it means that it has this extra information that it has the distance of di, absolute value of di, but the sign is actually, the direction is incorrect. It was supposed to be positive, but we are labeling as negative.
But is it DI always sometimes negative? Like if you go to the previous slide, isn't it? This is D is I that is greater than a constant, and the constant is negative.
So this means, this basically means that this equation, okay, so this basically means that we are on the right side and the margin is C.
So that's also true for the left side because of the sign distance. If it's negative, it's
Yes.
going to be multiplied by the label that is -1. So that makes
No, suppose what happens is that
Yeah, it's negative. It's the wrong classification.
the I is negative. So yes, so this is, suppose this is supposed to be, maybe I use it, this is supposed to be positive, but then this label is defined, or this height W is chosen such that points on this side has negative value. So the distance here, so there is a distance, say for example, distance is 5.3. But what is happening is that this sign distance is 5.3, but it was supposed to be, no, okay, so it's been confusing. Suppose, okay, so this would be negative, so sign distance would be minus 5.3, but the true label is positive 1, so we have positive 1 times minus 5.3, which would be some negative value. So that would be the situation. Basically, this whole D encodes two information. It's a distance to hyperplane, but also whether we are classifying that point correctly or not correctly. Yes?
Is TI the target or the classification?
CR is the target that we want.
Go back one question. So in your game, you have the sign of WDSI plus D equals to TI.
Mhm.
So that's the classification, right? It's not target.
That's the classification. So the classification is correct when what classifiers is saying is the same as what target is supposed.
I'm still asking.
Yeah. So there's a question, what's the effect of picking different C's? I get back to it. So, okay, so we got to this point that we want to, in order to maximize margin, we need to maximize the minimum of these distances. This is an optimization problem. We can also write it in this other form, constraint optimization, that I have here, which basically says that for all the constraints, all data points are equal to 1 to n, this di, so that's a di, should be larger than c. Okay, so that's a distance. That's a, if we find a c, say c point is 1 to 3, for example, and that satisfies all the constraints, it means that all distances, all distances are 1.3 or larger. Right? Now we are trying to find a C that is as large as possible, and we do this by maximizing over C. So we find a better C. For example, C becomes 2.1, so that is a better C. And we push this C as much as possible, which means that the minimum distance that we have, I mean the distances, or all of them is larger than, say, 2.1. Some of them might be larger, another one might be larger than another, say, J would be 2.5, and so on. But the minimum of them is at least C. You have a question?
Not anymore.
Okay, perfect.
Yeah.
Okay, so yes, there's a question.
So is this basically this person getting the example
So the question is that, is this trying to first focus on getting the classification correct and then maximizing the margin? I mean, the way I presented it is like this, but this is one optimization problem that if it is satisfied, it's at the same time, it tries to find the minimum distances and maximize that value.
Why ask if, like, for example, if I ignore one, we see twice with would this equation handle that? Would it be okay with specifying one?
Okay, so the comment was that, so what happens if we can ignore one point and make C much larger? So it might be the situation that, okay, so if we have so this is a good point. So if this is the, okay, so for example, and then the other labels would be different. So there is one particular point here. This one. That kind of is too close to the margin. If I could somehow remove this, then the margin would increase very quickly. So, I mean, my visualization is not perfect. This is not a balanced margin. But so that's the point. Now, this doesn't handle it. It just computes the minimum distance and then try to maximize it. But soon we will see a situation that actually we may need to do something like that. Okay, so maybe I go for this stage. So maybe it clears a few slides. Okay, so this was the objective that we had. We maximize C, the margin, such that the constraints, the distances, or all the margin of each point is larger than C, and we find the maximum value of C. So I want to do some kind of algebraic manipulations in order to make it, the optimization problem, slightly different and perhaps a little bit simpler. So just consider one of the constraints. So Ti times W transpose Xi plus B divided by the norm of weight. It says that it should be larger than C. So I just multiply both sides by the norm of W to get that Ti times this kind of not sign distance is larger than C times W, the norm of W. Okay, so we have, so this is equivalent. So if you now the point is that if you multiply W and B by any constant, like 5.5, for example, whatever, the inequality is still satisfied. So this basically says that the norm of W does not matter, which was something that I mentioned a few slides ago. And when we talked about W star, like if I multiply W by some constant small c in that previous slide, then it is still defining the same hyperplane. So the norm of W does not matter. So we can arbitrarily set it equal to some number, including 1 over C. So we can choose norm of W to be 1 over C. So if we do that, which equivalently we can write C to be 1 over norm of W, and simplify, we get something like this. So we're starting from here, but I choose the C to be 1 over norm of W, 2 norm of W. So I get my constraint is saying that the sign this di, with sign distance times that's the target value, is larger than 1 over norm of W, which I kind of reorder. I get that what we are saying is that Ti times W transpose Xi plus B should be larger or equal than value in 1. Okay? Is this clear? So what we did is we started from this point, this optimization problem, which is max margin objective, which has a C, and then we say that we could choose C to be equal to 1 over W, the norm of W. And then if we do that, basically, this means that I can choose it to be 1 over norm of W. And this optimization, maximizing this term, 1 over norm of W, is equivalent of minimizing the norm of W with the same constraint. So I don't write the constraint. So instead of maximizing 1 over norm, we can minimize the norm itself, which gets us to this optimization, which says that, okay, let's minimize the norm or norm squared, doesn't matter, of W such that Ti times W transpose Xi plus B is larger than or equal to 1. So this would become our max margin optimization formulated as an optimization problem. Maybe before I go on, can any of you recognize I get back to questions. Maybe I answer some questions because is C distance the closest point? C is the, okay, C that we have. Yes, C is kind of, if we have some value of C here, like 3.1, this basically means that the class is, that point I has distance of larger or equal than 3.1, and it has the right label. Why do we choose to replace C? I mean, the reason we chose it is that, well, I said that the choice of W is not important, so I can choose anything. I choose it to be 1 over a norm in order to do this kind of algebraic manipulation and get the formula that I want. So that's a kind of like a trick to make the optimization in form that we want. Okay, question. So do you know if you have this optimization problem? What kind of constraint? This is a constraint optimization problem. What kind of constraint optimization problem it is? Sorry. Okay, so it's convex. That's true. But can you be a bit more specific? I mean, maybe if you have taken an convex optimization course, you would recognize it, otherwise probably not. Anyone has taken optimization? I mean, people at ECE, I think you have an convex optimization course. We don't have it at CS. But anyway, so I just, okay.
Similar to the locally weighted regression. In this case, regularized because they're minimizing the normal.
So the comment is somehow related to local linear regression. I want to say no, because I mean, first of all, I don't want to talk about anything related to machine learning, but just in terms of constraint optimization. But there is an answer. Okay, so that is correct. But maybe just try to guide you. So the constraints are in the form of Ti times W transpose X plus B. What is the form of it in terms of W? Is it, what function is it? Is it quadratic, linear? It's linear and W. Okay, that's right. So we have linear constraints. So what about the objective? So it's quadratic objective. So if you have an optimization problem, which is quadratic in its objective and linear in its constraint, it's called quadratic problem. Or quadratic problem. Or QP. So that's right. Okay, nice. Sure.
Correction to that.
No worries.
When you're talking about maximizer, minimizer, you're always talking about optimizing its power, right?
Yes.
Always a number.
Yes.
That's why we're taking the norm there. Can you go back to this slide 14, please? So we are maximizing, minimizing the DI.
Yes.
But that's neutral number, that's not only one.
Which part of the minimum of I is a scalar, right?
So we are taking all the DIs and taking the minimum.
Yes. Yes. So
it's not, we're not minimizing what I, okay.
Yeah, I guess the question is that when we are optimizing something, we should always optimize some scalar, not a vector. And if that's the case, then why we have maximum of minimum? And my answer is that minimum is actually, like minimum has, we have n different values, we take a minimum of it, so it would be only one value. And that value, like minimum of a set of values is a scalar. So we are maximizing that minimum. Which is
the vector, we're taking the smallest element.
Yes, yes.
Okay.
But yeah, so it would be, you can, if say these are 1, 2.1, 3, 5.3, then the minimum, we are computing minimum of these, which would be 1. So minimum of that, so this should be equal to 1, and then we're maximizing over W. So here the distances, of course, depends on weights. So if I change weight, then each distance will change because I'm moving the hyperplane, so moving closer or farther from some points and vice versa for others. And that's the idea.
That's right. And given we're maximizing it, we're running only from negative values, which would be the mean multiplication.
Yes.
Okay.
Okay, so okay, so I guess we are almost, no, we are not almost done. But okay, so kind of visually what we are basically is doing, something happened. Okay, so it's kind of another visualization that we want to find a hyperplane that its margin is maximized. The margin is C, which is also equal to 1 over norm of W. So maximizing margin would be then equivalent of minimizing the norm of W, or norm of W squared. So that's what's happening. So this is the optimization problem. Again, I write it here. As I mentioned, it's a quadratic program, which is quadratic objective plus linear inequality constraints. One kind of observation is that I mean, maybe it requires a little bit of thinking in terms of constraint, but I try to convey it, is that if the constraint is not tight, which means that if for one of the xi's, if this value becomes, say, larger than 1, 2.3. So for that point, we say that the constraint is not tight, which means that it is not close to the limit of 1 that it satisfies. So 2.3 is larger than 1. If on the other hand, it was exactly, if for another point, so this is for another point xj, if we had it like 1, this value becomes 1. So 1 is greater or equal than 1, and the constraint is tight. So if the constraint is not tight, we could remove that that data point from the training set, and the solution of the optimization problem would be the same. So basically, in this case, in the case of, if for some xi, for example, for x10, 10th data point, we have this situation. If I remove that point, the optimization problem does not change because the constraint is already satisfied and it's not tight. So this is kind of just a remark that not all points in this set of inequalities are equally important. Some of them are important in defining what W should be, but some of them, even if you remove them, that does not matter. So the result is that these points, so those points that are kind of important in a sense that their margin, the algebraic margin, becomes 1, so they are tight for this inequality, they're called support vectors. So they are vectors that supporting that hyperplane. And they would be points that actually on the like on the margin, essentially. So for example, this would be one of them, and suppose this is actually, and this would be another one, supposing that star is actually on the margin. So in the figure, there is a little bit of gap. But these 2 points would be the support vectors for this constraint optimization. And that's why we call it, and that's why we call this method support vector machine. Okay, so few other comments is, I guess one other comment is that what is exactly support vector? Okay, what I defined, I think technically is more correct to call it support vector classifier, not support vector machine, and specifically hard support vector classifier. We see soon that there is something called soft support vector classifier and soft support vector machine. The difference between support vector machine and classifier is that if we do something called kernel-based computation, if it becomes a kernel machine, it becomes a support vector machine, which I'm going to talk about soon. But I think it is fair to even call these things support vector machine because it is a more common term, even if we are not using kernels. Yes?
Is the vector calculator from the origin, or is it like a perpendicular vector from the height?
You mean this, what I call support vectors? Yeah. Well, I mean, it doesn't matter. Yeah, so they are in some coordinate system. So they have X. So their name is just support vector. But yes, there is a coordinate system that defines dimensions of X's, and those are vectors with that coordinate system. But it doesn't really matter. You can translate everything. Another thing is that I want to mention is that we have methods that are like support vector machine or support vector classifier that are based on doing some kind of maximum margin, like define some form of margin and then try to maximize it. And those type of methods are usually called max margin or large margin algorithms or methods. We are not going to talk about them too much. Okay, so I think it's a good point for a break. Now is 14 past, maybe we can start 18 past. Okay, so we considered in the previous part, we considered the case that their data can be separated by a hyperplane. But what if there is no hyperplane or line in this figure that can separate data? So we have non-separable data points. So here, no matter what data points or hyperplane you choose, there would be always some points that are incorrectly misclassified. So you see that these points are incorrectly misclassified. And if you change that hyperplane, there exists no hyperplane that or line here that's separate. So here the idea is that, okay, so maybe we should allow some points to be within margin or even be misclassified, but we don't let them to happen a lot in some sense. So a bit more concretely, the idea here is that suppose we have this hyperplane and it has this margin that is shown here, and then you see that some points are within the margin. So for example, this point, this point, this point, and this point. These points are within the margin, and some of them might be, some of them are actually misclassified, right? So for example, use a different color. This one is misclassified because it's the wrong direction, wrong side of that line. This one as well. This one as well, but not this one. So this one is still within the right side, but it is within the margin. Okay. So what we can do is that we basically say that we allow these points to be within the margin, but then how much by some, say, values of x's. So xc1, xc2, xc3 to xc4. So this is x's which are positive numbers, is the kind of the distance or the amount that they pass the margin. So xc, if I show you xc1, would be like this value that is kind of separating, going into the margin. What we do is that we define these x's, which are called slack variables, but then we constrain or penalize the total amount of slacks. So we say that it is okay to have some of them violating the margin, but we penalize the summation of these x's, for example. So that's the basic idea, how we can do max margin classification for non-separable data points. So we need to change the constraints a little bit and also change the objective a little bit. So one way to do it is basically saying that we had this constraint before. If it was only C, it was basically saying that the margin should be at least C or greater than C. But now we are adding this 1 minus Ci term too, which basically says that, okay, it is okay to have some values that is smaller than C. So it would be C times, say, for example, C point is 0.2. So here, basically, it would be okay to be 0.8 times C would be the margin. And if C is actually larger, for example, than 1, for example, if we have 1 minus 1.5, this is actually the wrong classification. The right-hand side become negative. So that would be a point that on the wrong side of the margin, and this classifier would make a mistake on it. But that's okay. So, but we have a amount of slack variable equal to 1.5 here. So this is the part that we change the constraint. So this is called soft margin constraint. So instead of having hard margin, we make it soft. We allow some changes from that precise hard threshold. But then we penalize the sum of our slack variables. So we say that slack variables, the sum of them should not be very large. So how we do it? We just add that slack variable, or sum of them, to the objective. So the difference with before is that we basically after doing manipulations like before that, we start from C and then set C to be 1 equal, sorry, 1 divided by norm of W, we get to optimization that looks like this, which is the minimizing the norm as before, but plus this new term, which is the sum of slack variables and it is multiplied by some constant gamma, positive constant gamma, which basically says how much we want to pay attention to this norm and how much we want to pay attention to violation of the margins. And the objective becomes the same as before, except that now we have, instead of 1, we have 1 minus Ci. And Ci also should be positive or non-negative. Okay, so gamma is a hyperparameter trades off the margin with the amount of slack variables or sum of slack variables. So if gamma is equal to 0, we get W, the solution of this problem, to be equal to 0. Why is that the case?
Just so you get back over.
So because of the constraint, you're just subtracting the big left variable, which is always positive, so everything has negative variable.
Okay. I guess one comment is we get the original formulation, but it is not, because we have these slack variables too. So even though the objective becomes the same, but we have slack variables. So can you imagine why it might become 0? So I'm not sure if I heard you, but so basically the idea is, if there's no penalty on slack variables, if gamma is equal to 0, it means that we don't have any penalty on slack variables. So we can choose them whatever we want. So if we do that, we can always choose a large enough slack variables to make all the constraints satisfied, no matter what W we choose, right? And then because W part is penalizing the constraints, then what's the best solution, the minimizer, is when the W is equal to 0. So we can choose W equal to 0 and choose very large or large enough slack variables, because there's no penalty. That would be our solution. But on the other hand, if we get the gamma, make it large enough, the cost of our objective, choosing slack variable, becomes large. So we are basically trying to find W's that satisfies the inequalities. So one other comment is that this is one formulation of this objective. Another way, which basically I added the slack variable as a penalty. Another way is that we add the sum of slack variables as just a constraint. So we could have it the same objective. So we can have minimum of W, the usual constraints, but then also have, say, sum of slack variables would be smaller than some value, like lambda. So that would be another form of it, but I just write it in this penalty form instead of constraint. But you may see it in literature that there's other forms as well. Okay, so that's great, except that what now I kind of want to do, I mean, there's no except that part. I just want to start from this concept of margin violation to introduction of a new loss function. And that's, if you recall in the beginning, I promised that I introduce two loss functions during this lecture. One of them would be here. So we start from this, the constraints. So these are our constraints that basically we want slack variable to be positive, and the margin constraint satisfies to be 1 minus C. So remember that we have the penalty term on the slack variables in the objective. So basically we want to find the smallest slack variable. That penalty forces us to choose the smallest slack variable that these constraints are satisfied. So it means that we want to find the smallest slack variable C1, I, that satisfies both Ci being larger than the constraint given by data. So that's a margin, soft margin constraint, and also being Ci being not non-negative. So there are two cases that can happen. I mean, you can think about it. What does it mean about, okay, so now the question is that how should I choose C? What's the form of C? There are two cases that can happen. One is that if 1 minus Ti times W transpose X plus B is smaller than 0, then the smallest non-negative Ci, because Ci should be non-negative, that satisfies the constraint is Ci equal to 0. I guess you can convince yourself that's the case, because this side is non-negative, so the smallest value of Ci that I can choose is equal to 0. The other case is that if 1 minus Ti times W transpose X plus B is some positive value, then the smallest Ci that satisfies the constraint is that Ci should be exactly equal to 1 minus Ti W transpose X plus B. So depending on the cases, we either get that Ci should be 0 or should be some value that is positive. Ci can never be negative, which in other words, it means that Ci is the maximum of 0 and 1 minus this 1 minus Ti W transpose X plus B. Okay, so that's great. Now what we can do is that we change, recall that we had this sum of slack variables in the objective. We just replace this Ci with that, in that summation. So what we get is this summation of Ci becomes summation of maximum of 0 and this value. And the summation is over all data points i's. Okay? Is this clear what happened here? Perfect. So as some notation, sometimes people use maximum of 0 and some z, denoted by some z with subscript plus. So this basically chooses the positive part of z. If z is positive, it would be z. If it is negative, it returns 0. So this is just notation. So if we do this thing, basically we can change our objective of soft margin support vector classifier to this objective that, well, I denote zi's of W and B, which as just this W transpose X plus B. And then I put that term that I have, that Z into objective. So what we get is that we want to minimize W, B, and C's that are, well, minimize the norm of it, 2 norm of W squared, plus summation of the data of terms in the form of 1 minus Ti Zi, which is a function of W and B. And then take just the positive part of it. Yes?
I think in the square, it should be Xi.
Right. Yeah, I guess Yeah, I think we could define it at, no, actually, yes, that's true. Thank you. Okay, that's good. Yes, so Zi is the W transpose XI. Okay, so this is interesting because let's call this term that is in the form of 1 minus TZ positive part. This we can think of it as a loss function, and it is called hinge loss function. So this is a loss function of this how much our classifier penalizes essentially, or how much it violates the margin for ith data points. And then if we see it that way, then we see that what we are solving is finding W's such that summation of some loss functions, say Zi and Ti, plus some regularizer is minimized. So all this we start from margins and maximizing the margin, and then soften it and said that sometimes it's okay to violate it. If we do that, after doing this kind of argument in the previous page, we could convert that margin to some loss function. So what we get is a new kind of optimizer or new problem, which is having a special form of loss function, which is called hinge loss, plus some L2 regularizer on the parameter. So we can say that the soft margin support vector classifier can be seen as a linear classifier that uses hinge loss instead of other losses that we have seen, for example, cross entropy loss, and has an L2 regularizer. Okay, there was a question. Yeah, so I guess I haven't specified, but size should be still positive. Okay, sorry. Yep, no, I think we removed it, right? So there shouldn't be any size. Yeah, we removed size in previous. So there's no size. Okay.
So Z represents the linear.
Z represents this linear output of the linear passage, linear model. Any question on Zoom or here? Okay, so we can compare hinge loss with some other loss functions that we had seen before. So you've seen some version of this figure in the past in the lecture on linear model with classification with linear model. So maybe just I kind of point to a few of these. For example, for 0,1 loss function, here the loss would be 1 if the prediction of our class linear model Z is negative, and it is 0 if it is positive. So here the assumption is that the true target is +1. So that's the case. So we have other things like least square 1. This is the least square 1. You see that least square 1, the minimum is at 0.1. But for reasons that I kind of explained before, this is not a very good loss function. Because if Z is very positive, it means that the classifier is somehow very confident, which we can also think of it in geometric viewpoint that it has a large margin in the right side. But least squares cost loss basically says it is doing the wrong thing. So the other one we had was if you have a logistic regression, logistic activation function and cross entropy loss, that would be this red one, which if Z is positive, the cost function or the loss becomes smaller and smaller. And if it becomes very negative, the loss function grows. And the growth is almost linear. It's linear asymptotically. But this new one that we have, the hinge loss, the green one looks like this. So this is somehow similar. So basically saying that if the loss function, if the Z is larger than 1, so it has enough margin of 1, for example, then there's no loss. But if the margin is smaller than 1, it starts to penalize, and the penalty behaves linearly. So as soon as we start violating the margin, the cost in the objective would be proportional to the amount that we are violating. So asymptotically, these two are similar, but there is a shift where they start. And also the difference is that the hinge loss becomes 0 after if the margin is large enough. But cross entropy loss is trying to push us to be more and more confident in some sense. But hinge loss doesn't care as soon as we are on the right side and we have enough margin. So this is an important figure. We see another one in this course, I believe. Actually, the end of, I think, this lecture. I think it's a good summary of how these different loss functions would be. Okay, so this is support vector machine with linear models or support vector classifier. So we have a geometric viewpoint, and we got a loss function out of these discussions. And but there is still an issue. The issue is that we are still working with linear classifiers. And linear classifiers or linear models can be restrictive. Maybe they cannot separate the data points. So for example, here, if this is the input space, if I want to find a linear classifier, to classify them, I can't find anyone that does a very good job. But we can do something about this. And if you recall, we had this idea of basis expansion or feature mapping, which basically says that we can try to, instead of working in the original input space X, we map everything to some other space through using some function phi. And then we can do all the basic linear manipulations that we want, like linear regression, linear classification in that space. And this is basically what we can do. So here the idea is that if we find a good phi, maybe, we're projecting to some other space, maybe in that other space, things become nicer and linearly separable. Maybe not all necessarily always, but that's a possibility. So of course, one question here is that how can we find good features? Like previously we talked about some polynomial features, but there are Fourier bases, we can choose them and many others. So, but that's one question that generally we have to answer if we want to go through this path. The other question is that if the features are very high dimensional or maps the input to a high dimensional space, then the computation cost might become large. So for example, we'll see some examples, but suppose this is a two-dimensional, so X is 2, but then maybe after mapping this phi of X, maybe it belongs to R100 if the feature mapping is large enough. That increases the computation cost. And we actually see cases that can be very much larger. So just For example, if you want to have some boundary condition that is, or boundary, decision boundary that has a quadratic form, we can choose a feature which looks like this quadratic expansion. So we can choose phi x to be, like just as an example, to be like 1, x1, x2, x3 to xd, and then the pairwise combination of dimension I and j. So xi, x1, x2, x1, x3, up to xd minus 1, xd, and then we can have the quadratic terms for each of the x dimensions. So x1 squared, xd squared, up to xd squared. So this is one feature mapping that allows us to get quadratic decision boundaries. I mean, why that's important. But the issue here is that the dimension, number of these features, the dimension of the feature space becomes quite large. So it becomes order of d squared. So if the dimension of the input is 2, that's okay. But if the dimension of input is like 100, then our feature mapping would be order of 10,000, which can be quite large. So what we want to do is, kind of the roadmap is that we want to do this feature mapping without actually computing the feature mapping explicitly. It sounds a little bit unintuitive that how it is possible, but we get why it is the case. Okay, in order to do so, let's look back at support vector classifier, support vector machine once again, and try to reformulate it a little bit. So here I don't go into detail very much, so I try to finish it, go through it quickly, and I don't do all the computation, but I just give you the kind of general idea. Okay, so what we had before is that we had support vector machine that was formulated as this constraint optimization problem. So minimize the norm, we have some penalty and slack variables, and then we have a bunch of constraints which are soft. So this is called primal formulation of the constraint optimization. But in the convex optimization literature, we usually talk about convex primal form of optimization and dual form of optimization. I don't go into detail of what exactly they are, but I think it's important just to know that we can also try to solve the dual optimization. But the general path of doing that is like this, that in order to find the dual, we form the Lagrangian. So first we compute the Lagrangian for this constraint optimization. And if you recall, Lagrangian is essentially a single objective that puts all the constraints into one objective. So how does the Lagrangian looks like here? So Lagrangian, which depends on all the variables, is, okay, the objective itself. So we have L2 norm squared of W. We have the penalty term. But also we have each of the constraints coming in this form. So we have summation over all constraints that 1 minus zeta I, Ci minus Ti W transpose Xi plus B multiplied by alpha I. So this is the Lagrange parameter, or that would be the dual variable that we have. And then we have another set of constraints, which are Ci's should be larger than 0, which would be converted to this optimization. So you need to do some few steps of computation here, which basically you need to take gradient of this and equal it to 0 and try to solve. And if you do that, you get a formula that relates weights to alphas being these dual variables. And then you can convert the optimization, the primal optimization, to an optimization which only depends on dual variables. So they don't depend on W anymore. So the dual optimization problem looks like this. So it would be maximum over positive alphas of the summation over alpha i's minus summation over I and j from 1 to n of ti, tj, so target for data point I, target for data point j, so it's either positive 1 or negative 1, times alpha I times alpha j, times this term, which is xi transpose xj. So xi is the input of ith data points. It's a d-dimensional vector. We'll compute the inner product of it with the xj. And then there are some constraints that alpha I should be smaller than some constant c, and the summation of alpha I ti should be equal to 0. So I think just looking at this dual form, it is not obvious how we got that. But I think what is important here is that if we look at this objective, we see that data points, input data points, comes in the form of this inner product. So we only compute inner product of xi and xj. So that's all the information from data that we need. And if we compute the weights, we see that the weights can be written as summation of alpha i's, ti's, xi. So essentially, if we have alphas, then I can it somehow combines data points xi's in order to get the weights. And the prediction of support vector machine or classifier would be just the sign of W transpose X. So yi would be sign of W transpose X. And because you have the relation between alpha and W, so given the solution dual variables alphas, you get W, so you can compute this W transpose X. Okay, so this is the dual form without any feature mapping. If you add feature mapping, what we need to do instead is that instead of taking xi, first we map it to a feature space as phi of xi, and then we can do basically the same thing. The only difference would be that which xi's would be replaced by phi of xi's. So we get everything the same except that we have this term, which would be phi of xi transpose phi of xi. So what is the interpretation of this term? Okay, but what I'm kind of thinking is that well, if they're orthogonal, they get 0. That term would become 0. But what I'm looking, maybe it is not very clear. But what I'm looking is that this is, you can think of it as an inner product of phi of xi and phi of xj. Or another way is that we map xi's to feature space and then compute the inner product there. So that's what is happening here. So, yes.
I think the second one should be phi of xj.
It should be phi of xj. Yes, I guess it's not j. Yes. It should be j. Yeah. Thank you. Okay, so that's the optimization. So the optimization only depends on inner product in the feature space. And then the W's can be written as very similar to before. So before we had summation of xi's, now we will have summations of phi of xi's. And then the prediction of support vector machine would be the sign of W transpose phi. And if you plug in W here and expand, it would be essentially sign of summation of alpha I Ti phi of xi transpose times phi of x. So this phi of x comes from here. This phi of xi comes from the form of W. So you see that again, in order to compute the prediction of a support vector machine in this feature space, I only need to be able to compute phi of x, inner product of phi of xi with phi of x. And if I can compute that, then that's all I need. And the same for optimization. So that's a kind of the whole point here, that many support vector machine in particular, all the computation that it does in its optimization or in its prediction can be written in form of some inner product computation, inner product of something related to the input. Inner product, okay, so that's great. Inner product for high dimensional feature maps might be quite computationally expensive. So for example, in the previous case, if we choose phi x to be like this, the size is order of d squared, so the computation would be the order of d squared. But now, as I show soon, maybe we can actually avoid doing this inner product computation explicitly and do it much faster and easier. So just let's look at the inner product of phi of x and phi of y when phi is selected to be like this. Okay? Okay, so what's the inner product of that particular choice of feature map? The inner product would be, we can write it as phi of x and phi of y, would be 1 plus 2 times x summation of xi x yi plus summation of I on j from xi xj yi yj. I guess you can convince yourself that's the case. And if you do this, you can see that it gets a nice form. It can be written as 1 plus summation of xi yi, the whole thing squared. Which basically means that we need to compute the inner product. So what is this summation? This summation is the inner product of x and y in the original space. So if you compute the inner product in the original space, add 1. So this is a value, this is scalar. We add another 1 to it, so it's still scalar, and take it to the power of 2. So this is great. And the thing is that we can do this computation quite fast, because it's order of the computation of inner product in the original space, which is d-dimensional, is just order d. So we call this inner product. Okay, so that's great. So it basically shows that for this particular feature, we can do computation much faster without actually explicitly computing phi of x and phi of y. So here in this computation, I don't need to compute phi of x and phi of y. I just need to do some computation in input space. So the inner product in the feature space is called the kernel, and it's denoted by K. As here I'm showing capital K, but people use small k too. So inner product of K of x and y in the feature space by K of x and y. So this is called kernel, inner product in the feature space. So maybe I just use, okay. And now the important thing here is that we can actually sometimes define kernels without actually defining the feature space explicitly. So we can say that the inner product in some feature space is this function k of x and y, but we don't really explicitly mention what x and y is. So I'm going to give some examples, but I guess I don't have time for today, so we continue next time. So I believe maybe we should finish it during the tutorial time on Thursday. So I will record it if you can't attend. I want to finish this lecture this week and start to get to the middle of neural networks for next week, so I can release your homework before the reading week. If it is not possible, that's still okay, but I can release it, I think, early November. It should be mid-November that I could do this. So that's the plan. Okay, thank you very much.